So I was just quickly summarizing what we've done last lecture. We've laid down the foundations of information theory. We introduced the notion of Shannon entropy. We have shown through its definition and some of its properties that it's a good candidate for a notion of information content carried by a random variable. We've seen that it equivalently quantifies the average information content or the amount of uncertainty about this random variable prior to observing its outcome. We've seen then what's the Kullback-Leibler divergence, which is a notion of discrepancy between probability distributions. And we've seen that when using the Kullback-Leibler divergence to the joint distribution of random variables and compared with the product of their marginals, this defines the so-called mutual information. And we've seen that the mutual information is indeed a good notion of information content carried by one random variable about the other. And conceptually, we think of one of the random variable as the data, which depends on some unknown parameters, on some unknown signal to infer, and the mutual information has a natural meaning of how much the data depends on the signal and therefore how much information it carries about it and not about the noise, which is the complement of the signal in the data. Okay, so now I would like to bridge the first lecture on Bayesian inference and the second on information theory by showing to you that the mutual information is actually directly connected to the minimum mean square error, which is, as you recall, the error in the L02 sense, in the sense of Euclidean distance between the ground truth signal to infer, the unknown parameters to recover, and our estimator. And the best estimator that minimize in the average sense, in the Bayesian sense, that minimize the risk associated with the L2 loss is the minimum mean square estimator, the Bayes estimator, which is nothing else than the expectation, the mean of the posterior distribution. So I want to compute the error associated with this posterior expectation, and this I can do it if I know first how much information does the data contains about the unknown parameters, the signal. I will call it the signal from now. And this relation is the so-called IMMSE formula. Okay, so this is the fundamental connection between information and estimation. Okay, so the generic formula goes like this. So imagine that you have data y. So this y can be anything. It can be a scalar random variable. I mean, it can be a scalar variable. It can be a vector of observations, a matrix, a tensor. It doesn't matter. Will be observed, will be obtained as data plus Gaussian noise. Okay, so my data again is x, and the noise is z here. Okay, so the dimensions match, and this z is made of independent Gaussian entries with zero mean and variance 1. Okay, so the formula, the IMMSE formula, tells us that if I'm able to compute the mutual information between my signal and my data corrupted by Gaussian noise, then by simply taking the derivative of this mutual information with respect to the signal to noise ratio, this parameter lambda, which belongs to R plus, is called the signal to noise ratio, or SNR, which quantifies essentially the strength of the signal component in the data with respect to the noise. So if I take a derivative of the mutual information with respect to this SNR, I get directly access to the MMSE, the minimum mean square error, times 1/2, where again, the MMSE is the expectation, and here this is an expectation over everything. So this expectation is an expectation over the parameters to infer and the data. You can decompose it which you can decompose like this. It's signal and then conditional distribution of the data given the signal. Okay, which is equivalent to expectation over signal and expectation over noise. Okay, because this random variable y conditional on x is nothing else than the noise. Okay. So if I take an expectation there over everything of the L2 loss, the Euclidean distance between the signal x and the base optimal estimator of it, this is x base. This is given by this derivative. Okay, so we have a formula that directly connects a notion of information content, which is the information that the data carries about the signal, and estimation, which is the best error one can aim for when estimating x using the best estimator possible, which is the posterior mean. Okay, so this is really a fundamental relation that links estimation and information. If time allows, I will prove it. I'm not sure, but the derivation is surprisingly simple. So it's written in the lecture notes. I will show you where, but you can try by yourself. It's a simple exercise. I mean, once you see where to be careful in the computation, it's really simple. So it's an exercise. So let's discuss what this means. So okay, this we said. So what is important to know is that the mutual information as a function of the SNR, okay, in this model there, and the model we're going to study will be a model of this form, meaning that the noise will be additive and Gaussian, which is a very standard notion of noise. The mutual information seen as a function of lambda is an increasing function. And so the minimum mean square error, the best error we can achieve, is related to the derivative at a given point here of the MMSE. And therefore, the derivative is increasing, and of course, the MMSE is a positive constant. Sorry, it's a positive object. So this derivative is increasing, but this derivative is slowly decreasing as the SNR increase. So it's a concave function, and so therefore, as the SNR increase in this direction, the MMSE decreases as it should. The higher is the quality of the data, controlled by this signal-to-noise ratio. The more there is signal in the data compared to the noise, the lower should be the achievable error, right? And this formula says so, because this is a concave function, and so the derivative decreases as lambda increases. Okay, perfect. Any question on this formula before I move on to the next? Or is the meaning clear? Okay.
Sir, here,
yes.
In this, we are saying that as the gradient of this information function as a function of SNR it increases, the MMSE decrease. Could you please repeat it again?
Yes.
I was
so this relation here is not telling us that so this is the MMSE, right?
Yes, sir.
This is the best error we can achieve. What the formula tells is that the MMSE is related to the slope of the mutual information as a function of the SNR. So what we'll be able to show is that the mutual information is actually a function that looks like this, like what I represented there. It's a function that increases with lambda, okay? Because the more the data depends on x, the more the mutual information should increase by definition of what the mutual information is. So it's an increasing function, but at the same time, the slope decreases as lambda increase. So because the slope here is the minimum mean square error, it means that the minimum mean square error will go down as the SNR approaches infinity. In the limit where lambda goes to infinity, this curve becomes very flat, and here the slope tends to 0. I prime as a function of lambda tends to 0. And indeed, the best reconstruction error you can achieve when the signal to noise ratio tends to infinity should be 0. It means that you have no noise, and so you can perfectly reconstruct the signal. Okay?
Understood, sir. Thank you, sir.
You're welcome. Thank you for the question. All right, so let's now move to the definition of the main model we're going to study from now on. Okay, so again, I want to repeat that we're going to study a specific model, but many things that I'm going to say apply much more broadly. Okay, so there is not much of a loss of generality to focus on this model that is called the Spike-Wigner model, because it extends. Okay, so the first thing I want to mention is that this course is about a peculiar setting of Bayesian inference, which is called the Bayesian optimal setting. So what does it mean, Bayesian optimal setting? It means that as a statistician that tries to perform inference, you are using the correct prior distribution and the correct likelihood. It means that somehow it's an idealized model, an idealized setting, where the ground truth unknown parameters you're trying to infer are generated according to some probability distribution. Then there is a data generating process. You go from signal to data, which can be modeled according to a conditional distribution, P of y in x. And these distributions are both known to the statistician. So the statistician is correctly exploiting the prior information about the signal and is modeling the way the data generating model in the correct way. So there is the statistician is a kind of perfect statistician. They know perfectly how the signal and the data were generated. What they don't know is what is the precise realization of this signal. Okay, they think of this signal as a random variable with a certain probability distribution that they know, but they don't know what outcome of this random variable is out there. They want to recover this outcome. Okay, but these two distributions there are perfectly known by the statistician. Okay, what does it mean? Is that it means that the statistician can write down the Bayesian posterior distribution correctly. They can use the true posterior distribution of the signal given the data. Okay? And so this is what we mean by Bayesian optimal setting. Because you see, what I'm describing is a setting which is the best you can imagine. This is a setting where the only thing you don't know is the precise value of the signal, the unknown parameters, but you know how it was generated according to which probability distribution. So you know correctly all prior information there is to know about it. And you also perfectly model the way the data has been generated conditional on it. Okay? So this is optimal in this sense. And this is the setting that one should study in order to study the fundamental limits of inference. Because this is a setting where all prior and information, all the information is exploited correctly. We study the performance of estimators that are based on the correct posterior distribution. There is no mismatch, no errors, okay, no modeling error. And therefore, a statistician that places themselves in this setting should be able to reach the best possible reconstruction error. Okay? So we're going to focus on this. If you start to have mismatch, for example, a statistician that would assume instead of the true prior distribution Px, they would write down a posterior distribution based on, let's say, another probability distribution P tilde of x, which would not be the same. This is called a mismatch. And this leads, of course, to a decrease in performance of inference, of course, because you are making wrong modeling assumptions. But we're not going to consider that, okay? Perfect, so a very simple and at the same time profound implications of working in the Bayesian optimal setting is called the Nishimura identity. So Nishimura identities is a term that comes from physics, but in statistics, people simply call that the Tower property of conditional expectation. It's a thing you already know. It's very simple. This is this property there that you can write down. We already used it. You can write down a joint expectation with respect to data and signal, so y and x, as the expectation with respect to the signal times the expectation with respect to the data given the signal, or the other way around. The expectation with respect to data times the expectation with respect to x given y. So you see here, in this expression there, I should not think of the x random variable that I'm averaging over by this operator here as the signal, because it's kind of drawn conditional on y, so it should be thought as a posterior sample. This expectation is with respect to the posterior. So you see, it means that the full expectation can be decomposed as prior expectation times likelihood expectation, or as expectation with respect to data times posterior expectation. Okay, so this is called just the Tower property. And using this, you can get many simplifications. In particular, so here there is a generic theorem that you can take a look. But this theorem is basically telling you that if you take any function, forget this x2, xk. Let's simplify just a bit for the purpose of. Then you can read the more generic statement if you are interested. Let's say we have a function that depends on the data and on x, okay, where x is really the unknown parameters. It's the ground truth signal we're trying to recover. If I take an expectation of this function of y and x, both with respect to the posterior, this is what this bracket means, this bracket here, and I will use repeatedly this notation, so put it in your mind. The bracket will be a special symbol to denote an expectation with respect to the Bayesian posterior distribution. Okay? I will not use this bracket for any other type of expectations, only with respect to the posterior. Okay, so if I take, so I can write it like this, it's the same. Okay? If I take an expectation with respect to the data, this is an expectation with respect to the data, and with respect to the posterior of a function that depends on data and the ground truth x, then I can replace in it the ground truth by a sample from the posterior. This is what this x1 means. This x1 is a sample from the posterior distribution, not anymore from the prior. Instead, the x is drawn from the prior. Okay? So you see this Nishimura identity, which is a direct consequence of the Tower property here. The proof is one line. You can read it there. You can do that later. Is telling you that inside expectations, you can replace the true signal by a sample from the posterior distribution. Statistically, in average, they're the same. And this comes from the fact that we're considering this Bayesian optimal setting. The statistician is making no modeling error. Okay, and doing so, there is a statistical equivalence somehow between signal and samples from the posterior distribution. Okay, so one direct consequence of this, for example, is that the minimum mean square error, which is really we defined like this at the moment. Okay, so this is the average Euclidean distance between the ground truth X star and the Bayesian optimal estimator, which is the posterior mean, which I now denote with a bracket, as I said. Okay, this minimum mean square error can be written equivalently like this, which is actually the variance of the posterior distribution. The way you can see it to this Nishimura identity is the following. This, which again is this, is just a function of the data. Okay, this bracket is a function of the data only. I'm integrating over X, so it only depends on Y. So what I have is inside here I have a sample from the posterior distribution. This is this capital X that before I denoted X1. And while this is my ground truth generated from PX. I'm sorry, so there is a mismatch with the notation there. What I call capital X here, I will correct this in the notes, is what I call X star here. So it's a random variable drawn from the prior, not the posterior. And here what I denote X1 is this X. So I have a sample from the posterior distribution, a function of the data. So the Nishimori tells me, so I'm there, that I can replace, sorry, I'm there, I'm losing myself. I can replace this posterior sample by the ground truth, which are instead drawn from the prior. So I replace this by this X star, and so I obtain the MMSE. So we have these two equivalent formulas for the MMSE, which are just a consequence of this simple identity. Okay? Perfect. So this really is the variance of the posterior distribution. Okay. So if I ever mention in the next Nishimura identity, this is where you should look at, and basically I'm doing simplifications by interchanging ground truth, like unknown ground truth parameters with a new sample from the posterior distribution. I can exchange them like this inside expectations without changing anything. This is an important thing. All right, so I just told you that now I want to introduce this high-dimensional inference problem that I call the Spike-Wigner model that I mentioned quickly at the beginning, but I haven't defined formally. But before doing so, I want to study a much simpler problem, a much simpler inference problem, which is called scalar denoising. And we will see that actually there is a deep connection between the two, despite that what I'm going to present to you here is extremely simple. The scalar denoising problem is an inference problem over a scalar signal. So you have this unknown. So from now on, I will use a star like this to emphasize ground truth unknown parameters to recover, to distinguish this from, let's say, an X that would be a sample from the posterior distribution. Okay? So I'm measuring, my data is this single scalar, which is just my unknown X star times a signal to noise ratio, which is this square root lambda, plus Gaussian noise. This is just a standard Gaussian random variable. Okay? So this problem is very simple. There is a single variable to recover. We have a single data point. Yet it's important to understand, and we will see why. So let me just give you an example. So if the X star you want to recover is a Gaussian variable itself, so you have a Gaussian variable you want to infer which is corrupted by another Gaussian variable, which is noise, you can compute explicitly the mutual information, and it's a very simple formula. It's 1/2 of log of 1 plus signal to noise ratio times the variance of this signal, okay? I claim that the MMSC is the following, and how do I obtain this? I use the IMMSC formula. So I take twice the derivative of the mutual information, and this is very simple. You derive this with respect to lambda, and you get this, which by the IMMSC formula gives us the minimum mean square error. Okay? So very simple. Okay. So here there is a section where I prove this relation. This is also a denoising problem. You see, we have signal plus Gaussian noise. It's a bit more general because this is not necessarily a scalar variable in this case. When I put capital letters like this, which are not in bold, I mean generic variables, not scalar, not matrices, it can be anything. But it looks very much like the denoising problem. We have signal plus Gaussian noise. And so I used this formula to obtain the minimum mean square error from the mutual information. Okay, so this IMMSC formula that I just recalled you can be proven. I will skip the proof, but I recommend that you take a look. It's very simple. It's really about directly deriving, so writing down the definition of the mutual information, taking explicitly a derivative, and then doing some integration by part with respect to the noise variable. It's very simple, but the mechanisms that appear here are recurrent in this course, so I recommend that you try by yourself, okay, or at least you understand what is written there. So I will skip the proof.
Sir, may I take a moment to request everyone to please switch on their camera? I will take 1-2 screenshots if possible. May I request everyone to switch on their cameras also? Okay, sir, you continue, huh?
Okay. So let me mention that another example. So before I considered the signal, which is Gaussian distributed, corrupted by Gaussian noise. Let's consider now that the signal is not Gaussian. It has another distribution. It is binary. Okay. So this is telling us that with probability 1/2, the parameter we want to recover is equal to +1, and with probability 1/2 it is equal to -1. Of course, I don't know whether it was a +1 or -1. This is what I want to find back. So I'm trying to recover a random sign measured under Gaussian noise. Okay. You can, using the explicit definition of the mutual information that I write here, starting from the difference of entropy of the data minus the entropy of the noise. Remember the previous lecture. Here you can do a bunch of simplifications, and you will arrive at a generic formula, which you can derive. You get the MMSC. And in the case of denoising a binary variable, you obtain a slightly more complicated formula than before, which is now still with an integral there. You cannot fully simplify it. It remains an integral with respect to a Gaussian variable z. And it is the following. It's 1 minus expectation of the hyperbolic tangent of the SNR plus square root of the SNR times this noise to the square. And here you see it looks like I've done a typo. I'm writing an equality, and I have the very same formula, but there is no square here. This is not a typo. This is actually a consequence of the Nishimori identity. So if you do things correctly, you would realize that these two things are equal, and this is a basic simplification implied by this Nishimori identity I discussed before. Okay, so we have two formulas for the MMSC of scalar denoising problem. One when my signal is binary, and 1, much simpler, when my signal is Gaussian distributed. So I can just plot these two functions. I will take sigma squared equal to 1 here. We'll take a standard Gaussian variable for my signal. I can plot these two formulas as a function of the SNR lambda and see how they look like. Let's do this. They look like this, okay? So this is this function for the denoising problem as a function of lambda, the SNR, okay? So there are different observations we can make here, okay? The first one is that these two quantities, they start from 1 when the SNR is 0, okay? And this is simply telling us that when the SNR is 0, so basically the data we have access to is pure noise, the only thing we can do is trust our prior, because we have no data, essentially. This is pure noise, okay? And we know it, because we are a Bayesian optimal statistician, so we know the value of this SNR. Forgot to mention, but in this Bayesian optimal setting, knowing the likelihood means knowing also the SNR, of course. So because you know that your data is just noise, you're not exploiting it, the best you can do is essentially exploit the prior. And the mean with respect to the prior, in both cases, is 0, because the Gaussian variable has 0 mean, and our Rademacher variable here has also 0 mean. So the Bayesian optimal estimator when you have 0 SNR is just to output 0. And the error of such an estimator in average is 1. Okay? And then when the SNR increase, the error decrease as it should. Okay? So the other thing we can notice is that the Gaussian curve is above the Rademacher curve. And this is natural, right? Because the Rademacher prior is a much more informative prior than the Gaussian. A Gaussian variable can take any value between 0 and plus infinity. It has very small probability to be too large, but still it is a like a continuous random variable with an infinite support. Instead, the Rademacher variable is telling you that it's or a plus 1 or a minus 1. So somehow you have much more information, right? So it is natural to see that the Rademacher minimum mean square error, I mean, in the case of Rademacher prior, is below the one of the Gaussian case, okay? And the third thing we can notice is that these curves are very boring. They're not interesting at all, in the sense that there are nothing special we can notice apart from the fact that they are smoothly decreasing functions, but we don't see any interesting behavior. And by interesting, I mean, for example, a discontinuity or at least a cusp. You see a point where it would be non-analytic. We don't see any such behavior. It's just a boring, smooth curve in both cases. Okay. The reason that these curves are boring is that, of course, the problem we studied is way too simple. This is a very simple inference problem. There is no complexity, okay? So by complexity, I mean two things. And this is also what physicists mean when they, in statistical physics. Complexity means that we should consider inference of many variables. So we should go towards high dimension. And these variables should interact somehow. They should not be independent, because of course, if you are trying to infer unknowns which are completely independent and your data does not mix them, does not couple them in any way, you are simply trying to solve independent scalar problems. So we need many variables that are somehow coupled, that are dependent on each other through our observations of the data. Okay? And so this is where the Spike-Wigner model enters into play. Okay? So this is where interesting things will now happen. Okay? We hope that some more interesting behavior than this smooth MMSE curve will emerge, and this will be the case. Is there a question before I go towards the high dimensional problem?
Do we have any questions from the audience?
Okay, there's not. I will
Okay.
continue. All right. So here is the Spike-Wigner model. So memorize it, put it in your hand, because for the next 4 days, you're going to study it in very much details. Okay? So this is an inference problem where now the data, Y, is a matrix of size n by n. It's a symmetric matrix. The signal, the unknown parameters to recover is this x star. It's a vector of dimension n. The noise is a symmetric Gaussian matrix. Okay. And the way the data depends on the signal and noise is this model there. So basically what you do is that you take what you observe are noisy versions of the pairwise products of the entries of the unknown vector. Okay? You take a product xi star, xj star, you multiply it by signal to noise ratio. You also scale down its amplitude with this 1 over square root n. I will explain where it comes from, where n is the dimension of this vector, x star. You corrupt this by noise, and this is your observation. And you do that for all the possible pairwise products between the components of the vector. Okay? So why is this called the spiked Wigner model? It is called so because a matrix like this, a matrix which is symmetric, whose entries are independent Gaussian, is called a Wigner matrix in random matrix theory, and we're going to study it in detail tomorrow. Okay? And this part, the signal part of interest, which we try to recover, is called a spike. It's called a spike because it's a rank 1 matrix. Okay, so matrix-wise, you can write it like this: x star transpose. A rank 1 matrix like this is called a spike. So this is a spike model because you have a full rank noise matrix, which is perturbed by a rank 1 spike, and you're trying to recover the rank 1 spike from the sum of the two. Is the model clear? Please stop me if it's not, otherwise you will suffer for the next 4 days, or it will make no sense to continue. So if the model is not clear, just ask. Okay.
Excuse me, sir. Am I audible?
Yes.
Sir, I have a question.
Go ahead, yeah.
Hello. Yeah. So xi star and xj star, you were telling that this is the unknown these symbols are for the unknown parameters, right?
Yes.
Okay. So if we are adding the x summation like xi and xj for the unknown parameters and adding with the zij, so like what is its real like meaning and the significance? How like can we interpret from this? What is this exactly saying? Like I'm not getting it.
So sorry, I don't think I get your question. What your question is what's the meaning of this, or?
Yeah, like what is the role of this zij with this unknown parameter of xi and xj?
So okay, the zij here represents noise. It represents the component in the data. So this is the data that you observe. This is the only thing you know as a statistician. This is the unknown component, and this is the noise. Okay? You don't know X star, you don't know Z. The only thing that is given to you is this matrix Y. And your task, the inference task, is given this Y only, and the knowledge of how the Y was generated conditional on X star. So you know this model basically, but you don't know X star and you don't know Z, and you want to recover X star from the Y. Is it clear?
Okay, but sir, like one more thing in this same question, like how we are taking only xi star and xj star as a unknown parameter only for
No.
like.
No, it's not just xi star and xj star. You measure these yij's for every I and j running from 1 to n. You have many observations for. Yeah.
Yeah, okay, 1 to n. So for that, my main question is like, why only the product of x with I and x with j? Why not with another variable? Like same variable, why we are taking? Just because we are having the same matrix, that's why.
Because we are having the same what?
Yeah, like I'm assuming like that we are having this operation inside a one matrix like Yij. That's why we are taking like the Xi star or Xj star, or is it having some different analogy?
So I mean, your question is why is the model like this, right?
Yeah. That's what I'm asking.
Yeah, I mean, simply it's my choice. It's a model that I find interesting to study. Now I will give you applications of this model. But what I claim is that studying this precise inference problem allows you to understand very many practical settings that I will show you. Okay? So assume that this is an interesting model. You could study infinitely many other models, of course. But I claim that this is one which is very rich, that at the same time you can fully understand, and that has many applications. Is that a valid answer?
Yeah. Okay.
Okay,
Thank you.
perfect.
I had one more question.
Yes, please.
What is lambda?
Yeah, lambda is like before. It's my signal to noise ratio. It controls the strength of the signal part, which is this rank 1 matrix, with respect to z. You see that if I take lambda going to infinity, basically my data
Is
becomes only signal. This becomes irrelevant, right?
Mm-hmm.
If instead lambda is 0, this is the opposite. Lambda equal to 0, there is no signal part anymore, and the data is pure noise. So the signal to noise ratio controls the signal part in the data. Okay.
So I imagine, as lambda goes arbitrarily small, does this algorithm work that you can recover x?
So we are going to study algorithms.
This is sneak peek, yeah.
Yeah, exactly. So the whole point of the course is to understand how well can I infer this part here as a function of lambda. This is the whole question.
Mm-hmm.
Okay.
Perfect.
So we will see that the answer depends on which algorithm you're considering and the cost you're ready to pay in terms of computation. Okay.
Okay.
So we are trying to first fitting up these equations as their model, and then we are going to test it in under various situations, like how it is suitable for different situations and circumstances in this segment.
Yeah. So it's a kind of abstract general model, and I will claim very soon that it is important for many applications which are relevant in signal processing, in machine learning, in many contexts. Yeah. Okay. Okay. So here is the model we want to study. Okay, that I wrote here in matrix form. So do you all hear me, or is it frozen? Hello?
Yes,
Yes,
sir,
sir.
we can hear you.
Hello, yes, sir, you are audible.
Okay, I'm back. Perfect, perfect. Thank you. All right, so this is our model. Perfect. So assume for the moment that it's an interesting model. I will show to you that it's the case. Let's assume that's the case. Let's write down, let's exploit what we've done in the previous lecture. Let's write down the posterior distribution. Okay? So the posterior distribution is written there. This is very simple. It's the prior. So I will assume that in this model, I will even simplify further this model. I will assume that the entries xi star were generated IID independently and identically distributed from my prior PX. Okay? So this is a modeling assumption that I assume is correct. This is the setting we're studying. So my prior distribution is there. It's a product measure over all the components weighted by the correct prior times a Gaussian likelihood. Okay? So you see that for every observation Yij, I have a Gaussian weight, and this Gaussian comes from the fact that the noise Zij was Gaussian. Okay, so this is saying that the noise is Gaussian is the same as saying that my observations Yij were generated as Yij conditional on X star was generated as a Gaussian with mean square root lambda over n xi star xj star and variance 1. This is another way to rewrite the Spike-Wigner model. It's exactly the same thing, right? Because this formulation is equivalent to say this. You see? Adding a Gaussian noise of variance 1 to this shift, which is like a mean, is the same as saying that Yij, conditional on this, has this mean and variance equal to 1, right? Okay, so this is my likelihood. This is my likelihood distribution. And so, it's what's written there. I have a product of exponential, one for each observation, which I can put as a sum inside the exponent from the property of the exponential. I have an exponential of sum over ij of Yij minus square root lambda over n xi minus xj. Okay, this is this distribution there. Yij is a Gaussian with this mean and variance equal 1. So here is the mean and variance equal to 1. Okay, is it clear? And this is just the normalization of the Gaussians. Okay, and this proportionality symbol means that this is an equality up to a missing normalization constant that I should write down correctly. But is it okay for you? Do you understand the form of this posterior distribution? Prior times the likelihood of each observations. Okay? Perfect. Let me give you a few motivations. So there's been many questions on why is this model useful. That's a very valid question. So let me motivate it in different applications. So this model was originally introduced by statisticians around 2010, but it was studied earlier by people in random matrices as a simple probabilistic model for what we call sparse principal component analysis. So I think you all know what principal component analysis is. It's about taking an array of data, a matrix of data, and trying to find some principal components, meaning some relevant linear combinations of the columns of this data that you can think of as features, where the rows are samples. You are sampling points which have different features, And you are looking for linear combinations of these features that can explain most of the variability of the data, but using just one direction, just one vector instead of a whole basis of features. You want to find a special feature, which and this is PCA. And this is a model for PCA because you see, this is like we have noisy data. This is the noise component. And this is the hidden special direction. It's a rank 1 matrix. So we're looking for X star, which is a single vector, which will capture the information part. It's a special direction we're trying to recover. So it's like PCA. And if you assume that the entries of this X star are sparse, so it has many zero components, so this hidden direction that you're trying to find lives on a subset of the ambient space on a lower dimensional manifold. Only few components are non-zero. This is sparse PCA. Okay, so it's a very important problem in signal processing. Okay. Another problem I want to mention there is community detection in the stochastic block model. So I won't explain how the connection is made, but I will explain you what it says. The stochastic block model, so community detection, what it is, it's a problem, it's an inference problem, where what you observe is a graph of interaction between nodes. Okay, so you have a graph. And what you assume is that somehow in this graph, there are communities that are hidden. It means that some nodes can be kind of clustered together. They share some property. While some other nodes, they belong to another group. They share another property. So think about observing, for example, the graph of connections among people on Facebook. Okay. What you know is that on the Facebook network, there are people that vote on the left, and there are people, the voters for the right wing, left wing. Okay, and your hypothesis is that people with the same feature, so let's say that vote for the left, tend to be more connected to each others. And this is natural indeed, right? You tend to be friends and therefore to be connected on Facebook with people, more likely with people that have the same opinion as you, so that will vote the same party, right? So these are the two communities that you're trying to recover. And the inference problem is given this observation of the graph, which you can think as a kind of noisy data, because of course you will also be connected to people that vote differently than you, which you can think as a source of noise. It disturbs inference. Given this noisy graph, can you recover the communities? Okay, to which node, to which party a given node will vote for? This is a very generic problem. Or for example, in ecology, you can measure, you can observe that some species, which are the nodes on the graph, interact with each other. Some are predators, some are preys. Preys and predators tend to interact because one is hunting for the other. There are species that do not interact at all, etc. And given this graph of interactions between different species, you are trying to cluster the species into groups which have various meanings. Okay. Surprisingly, the theoretical study of this community detection problem is fundamentally linked to the study of the Spike-Wigner model. Okay? Somehow you can, I mean, at a naive, at a simple level, the connection, let's say, it doesn't look crazy that there is a connection with this problem, because you see, you can think of this as a kind of variable that tells you whether two nodes, if you now think of these components of these vectors as representing nodes on a graph, you are observing kind of interactions between nodes on a graph, which have been corrupted by noise. and you are trying to recover the state of the nodes. Okay, so if you now you say that every X star component can be plus or minus 1 to represent group 1 and group minus 1, or blue and red, or prey and predators, you are measuring graphs of interactions between these groups, and you're trying to recover which node belong to which group. So it's naturally connected to community detection. Okay. So, and which is a whole field in itself, by the way. Community detection, people do their entire career on studying this problem. And the way we understand the fundamental limits of inference in this community detection problem is through the analysis of the Spike-Wigner model. Okay. Another important model is high dimension. Maybe I will explain this one. This is a classical example. It's called the spike covariance model. So if you slightly generalize the Spike-Wigner model, where you say that now the rank 1 matrix is not anymore symmetric, so you have two vectors, U and V, and what you are measuring are noisy versions of the pairwise product between component I of vector U and component J of vector V. Then this model is equivalent to say that what you observe are Gaussian vectors, which are the columns of this matrix of observations, which have zero mean and whose covariance is basically the identity plus a rank 1 matrix. So you are trying, basically it's like if you have a noisy covariance matrix and there is a hidden spatial direction in this covariance which you're looking for, and the strength of this hidden direction is controlled by this lambda there, and this hidden direction is this vector U. Okay, so this is really a model for finding hidden direction when doing principal component analysis. Okay, it is also related to clustering, high dimensional clustering. You can read a bit, but I need to move on. So I hope what I convinced to you is that somehow the Spike-Wigner model is interesting. It's a very general model, and depending on the choice of the prior distribution for the signal, you will model this or that specific problem. Okay. There are many other applications. So I think that time-wise, it's been an hour. Should I continue a bit, Jaspal? I'm not done with everything I wanted to say, but I can also stop there and say a bit less. I mean, I don't have to finish everything every time. So.
Actually, sir, the team who is doing recording has to leave in 5-10 minutes. So you can take 5 minutes to wind up, and we can start tomorrow. If you want, we can start tomorrow, resume from here.
Okay. So if I have 5 minutes, maybe I can state the main results, one of the main results we're going to derive. So first, is there any question from anyone on this Spike-Wigner model? Okay. So the Spike-Wigner model, think of it as the most paradigmatic model for extracting hidden low-rank structures in high dimensional, in large noisy matrices. And of course, given that data in modern applications always come in the form of large matrices, where there is some hidden structure there, it is very general. Okay, so that's the motivation for it. Okay, so what is the main result we want to get? This result is called the replica symmetric formula. So forget what the name means. This is not so important. This is just a terminology that comes from statistical physics. Historically, we call this kind of formulas in this way, but think of it just as a formula for the mutual information of the Spike-Wigner model. This is what it means. Okay. So this theorem which I have proven with colleagues during my postdoc based on mathematically rigorous techniques we developed, which I will not explain during this course. Instead, I will show you an heuristic derivation based instead on physics tools, which you can then prove using other techniques. But I will focus on the physics tools. It would take a whole course to prove these kind of things, but trust me, this is a theorem. This theorem is telling you the following. The mutual information between this rank 1 matrix, the spike, the information, and the data, divided by n, okay, which is the same as the mutual information between the data and x star itself. So why is this equality true? Simply because the data depend on x star only through x star transpose, only through this rank 1 matrix. In case this is not clear, this notation simply means x star transpose, which is an n by n matrix. It's a row times a column. Sorry, it's a column times a row, so it's a matrix whose elements are xi star, xj star. Okay, so the mutual information between signal and data is given by a pretty simple formula, which is an infimum with respect to some parameter that we call q, that belongs to 0 and rho, where rho by definition is the second moment of the prior. Yes. Okay. The infimum of a certain function that depends on this parameter to optimize over and on the signal to noise ratio in the problem. Okay. And this function is called the replica symmetric potential. Again, this is just a name. It's a certain function which has the following nice form. So let's focus on this part here. So there is a very simple term there, which is just quadratic in Q times the SNR. And what appears here, now you should recognize, this is the mutual information of the scalar denoising problem under Gaussian noise. You see this x star here, you should not think anymore as the vector. For the vector, I use a bold variable. It's just a single scalar random variable drawn from the prior. It's written there. And this z is just a single scalar Gaussian noise. So this formula is telling you that somehow there is hidden in the high dimensional problem of interest, the spike-Wiener model, a kind of reduction in complexity when in the so-called large system limit, when n goes to infinity, where n is parameterizing the size of the signal to infer, and therefore the size of the data matrix. This is an n by n matrix. So when the problem size goes to infinity, the very high dimensional object corresponding to this mutual information, this is a very complicated object, somehow reduces onto this simple formula. And in this simple formula, there is in particular something we recognize, which is the mutual information of a single scalar denoising problem. Okay? So this looks very weird. How the hell could it be that this high dimensional complicated problem where all variables interact with each other through the data could collapse on such a simple problem? So we will see first that even if this simple problem appears, the problem does not trivialize, okay, through this infimum operation here, which hides complexity. And interesting things can happen. So I will try to show you, to give you some, let's say, to try to convince you how does this happen, and we will see towards the last lecture. We will show this result and we will understand the mechanisms behind this reduction. But so what I want to say that I forgot. No, I forgot nothing, I think. So yes, so that's the main goal. One of the main goal of this course is to understand why is the computation of this mutual information reduces to such a simple problem there, okay? And this is really at the core of what we call the mean field analysis in physics. This kind of dimensionality reduction from very high dimensional problems to kind of effective low dimensional problems is typical from mean field analysis in physics and generally in what we call high dimensional statistics, in modern statistics. Okay, so we're going to understand that in the next lectures. Okay, I think that's enough for today. We will resume. Okay, I'm already late, so I will have to cut a few things, but tomorrow we'll spend at least 2 lectures on this chapter on random matrix theory. We're going to study the performance on this problem of a very simple algorithm, which is spectral PCA. So you can already take a look if you want. Okay, so then see you tomorrow, except if there are questions.
Is there any questions? So tomorrow we are starting at 11:40 IST.
Yeah. Perfect.
As in the schedule. I may also request everyone to kindly switch on their camera so that let us take one last screenshot for the day. If you all, sir, you may please stop sharing your screen so that we can take one screenshot.
Okay, you want me to stop sharing?
Do we have questions? I request everyone to please switch on your camera so that I can take everyone in one screenshot. Huh? Thank you.
It's nice to see real faces.
Yes.
Hello, everyone.
And I request that you may switch on your camera. It gives the lecturer more interest that if we are able to see, I think it creates more interest. So you may switch on your camera even throughout so that we can see each other and learn. So with these words, I would like to express my sincere gratitude to Professor Jan Barbier to spend one full day with us. Thank you, sir. Thank you for your kind insights. And I would like to thank all the participants for patient hearing. And we will see you tomorrow at 11:40 a.m. as per schedule.
Have a good rest. It will be
Thank you. Thank you, sir. Thank you, everyone. Okay, bye-bye.
Thank you, sir.